To push further the idea of a trapezoid and see if we get anything better, we're going to develop something called Simpsons Rule, which of course has nothing to do with the character of the cartoon TV program, but with a mathematician whose name was Simpson. What is the idea here? Okay, this time what we're going to do is we're going to use as tops of each slice not flat horizontal lines, not slanted lines, but quadratic functions, so parabolas. Okay, now so what we're going to do is we're going to take our region and we're going to slice it as always, but we need to slice it in such a way that we need to come up with parabolas. Well, in order to identify a parabola, you need 3 points. Okay, for each parabola, every time we want to identify some parabola, we need 3 points on it, and that means that we are going to have to use 2 slices for each parabola. Right? So what we're going to do is we're going to use these 2 slices. Those 2 slices give us 3 points as the intersection of the vertical lines and the function, if you want, as the value of the function at those 3 values. And so those 3 will generate a parabola. Fine. So what we're going to do is from now on we're going to use 2 more slices. Okay, that give us 3 more points, and they're going to generate another parabola. Now those might not look like parabolas, but believe me, they are. And then finally we have the last 2 slices, which again are going to generate another parabola. Notice how good this one looks. It's actually very difficult to distinguish this set of parabolas from the actual curve that we had to begin with. Okay? Now, but this process suggests that in order to use this rule, we are going to need an even number of slices because we have to take them in pairs. Okay, but if we do that, we can actually calculate the area under each one of those parabolas. That's easy. I mean, we know how to calculate areas under parabolas, right? And we can put them all together, do a little bit of algebra, which I'm going to spare you, and we end up with a final formula which is not too bad. Well, let's have a look at what this final formula looks like. All right, so for the formula for Simpsons rule, it looks like this. The integral from a to b of f of x dx using Simpson formula is approximately given by don't panic. This looks like a complicated formula, but it does have a pattern. Okay, so let's look at the pattern. First of all, notice that we have the first and the last points, the first and the last values, x0 and xn, they are only considered ones. Then all the points which are sort of the odd points in the sequence, so x1, x3, etc., up to the second last one, xn minus 1, they're all multiplied by this coefficient 4. Where does it come from? It comes from all the algebra and number crunching that I've spared you. And the ones, on the other hand, in even position, like that f of x2, and then if there is one, x of x4, x6, and so on, they will have a coefficient of 2. So in other words, the formula that we have in there tells us to compute the value of the function at all those dividing points of the slice, and then multiply them by coefficients according to the pattern 1, then 4, 2, 4, 2, 4, 2, as many times as you have slices, and then 4 as the second last one, and then once again for the last one. Now remember, n is supposed to be an even number, so n minus 1 is going to be an odd number, and that's why the second last one is always going to be multiplied by 4. Notice also that this time in front here, instead of having b minus a over n, which is our delta x for the midpoint formula, or b minus a over 2n, which was the delta x divided by 3 for the by 2 for the trapezoidal formula, we have a 3 in there, and that corresponds to the fact that for each of the parabolas we need 3 points. Remember, for the trapezoid, for each of the trapezoid we needed 2 points, for each midpoint we needed 1 point only. Now for this parabola we need 3 points. So this one, does it work better? We're going to see in a minute that yes, it does. Okay, and we're also going to see that by experimenting with a number of situations. So trapezoid, doesn't look like it's very good. Simpsons rule, even from the example I just gave you, the visual example, it looks like it should work very well because the parabolas tend to hug the curve very nicely. Can we do better? Can we use higher degree polynomials? Can we actually use, say, cubic polynomials? Yes, we can. It can be done, but the problem with that is that actually we end up with some really cumbersome formula. Okay, there is something algebraically going on with Simpsons rule and the use of parabolas, which simplifies things quite nicely. But for cubic and higher polynomial, those simplifications do not occur. We end up with a formula which is really unwieldy, and so it may be better to actually stick to Simpsons rule at most and increase the number of slices rather than going to a more complicated formula. However, there are more numeric methods which are more advanced, which we're not going to see in this course, but that you might see in a later mathematics course. And so, for instance, these are the methods that are used in some calculators or computer programs. So things can be improved even logically, even in terms of efficiency and so on. But as far as doing things possibly by hand, Simpson's rule is as far as we're going to go.